I'm Sam. I'm a product manager with PingCAP. I've been here 2 months, so I'm excited to have been hired just in time to be at this talk or at this conference, but also give a talk at it. So before I get started with the actual how good is my HTAP talk, I have a survey for you. I think, sorry, let me go back. In my opinion, I think it's the opinion of some other people that the term online, when we're referring to data, OLTP, OLAP, right, is sort of, it's a little wishy-washy these days. I think people are defining it differently or treating data as online when it might not be, or vice versa. So I have a survey for you guys. It's that you can't be wrong about these questions, but I'm just curious what people think. So daily forecasts, this type of data, would you consider this to be online or offline? And raise your hand if you think it's online, and hand down for offline. And if your hand is down because you don't know, I'm going to count it as a no, and my data is going to be dirty. Cool. I see no hands. That tracks with my experience. How about business intelligence dashboards that are refreshed on a minute basis? Online. Okay. How about an application that exposes user-created data in real time? Cool. Application that exposes user analytics in-app in real time. Okay. Well, hey, funny you say that. Funny you say that is this one has no quotes. So, yeah, that's a trick. I had to get people on something. You know, this is a subjective test. Anyways, okay, so that's good. I've logged all that data, and I'm gonna analyze it later. But my definition of online, just so like you can disagree with this, we can talk about it later, but it's just to going forward and to have a definition to work with is data is real time and it's user exposed, basically, right? Anyways, all right. So first thing I want to do is I know it's HTAP Summit. Everyone's talked about HTAP, so I'm going to zoom through like a what, why, when HTAP. I just think it's good context. And then the meat of this is the second and third, which is basically kind of stuff to think about when you're evaluating an HTAP system, and then actually introducing a tool authored by University of Wisconsin to do that in a more programmatic way called HATtrick. And then lastly, I'll just cover us doing this benchmark with TiDB and kind of show you the results there. So on to the what, why, when of HTAP. Again, zooming through this little HTAP introduction, everyone who's here probably has or is in some way related to some sort of system of record. Their application is a system of record, or they have a set of systems of record. And then behind that somewhere or next to it is some sort of reporting, right? Some sort of analytics. It could be back office reporting. It could be dashboards that are being looked at by executives. It could be real time. It could be not real time. But generally speaking, we consider both of these things to be sitting on top of two different data stores, right? We have on the system of record, we have like an ODS, an operational data store that's usually OLTP, sometimes ACID compliant. It's row oriented usually. Behind the reporting stuff, we have something analytical, right? And usually columnar. The assumption that we make today in most cases, I know there's exceptions, is that there's some process in between those two things, some amount of extra infrastructure and jobs that are going on to move data from one place to the other. In the case of actually moving OLTP data to an OLAP system, right? And then because of that, there's actually non-zero amount of time in between the data arriving in both places. So based on the definition I gave you earlier, I don't personally consider this to be OLAP on the right here, right? I don't consider this to be online because the data is not actually being served in real time. There's some amount of non-zero latency between OLTP and OLAP. This makes our users sad, right? Like as a product manager, users, especially if my marketing team or my website says that we serve in real time and our users expect that, we're not actually doing it. And if they kind of figure that out, it's no good for us. What if we combine the analytics and the OLTP into an application, into a hybrid application? I don't know if you guys were at the Catalyst talk earlier. The Catalyst is kind of like this. Any CRM is kind of like this, or some Web3 applications where they're doing transactional workloads as well as serving analytical queries in the app in real time. Sorry, I think I have an extra slide here, but the idea here is that you actually have an application that your developers are working on that are where they're interfacing with two data stores, or at least two data stores, right? The OLTP one and the OLAP one. And that makes your developers sad, right? They don't want to, I mean, we have savvy developers who can do that, but like generally speaking, we want to probably reduce the amount of interfaces that they're working with. So we fix this generally with some kind of middleware, right? Something that unifies the APIs. I think Proxy SQL might be one of those, and that was a talk just a second ago. Where basically the developers only have to interact with one thing. But that doesn't solve all our problems because we still have the infrastructure to deal with, the ETL jobs and things like that. So we still have sad back-end engineers, right? What we want to do is get rid of it all. And to do that, the proposal, of course, is an HTAP data store. So that's kind of the HTAP pitch there. When you introduce HTAP, I mean, all those people become happy again, right? So that's the story there. So when you introduce HTAP, you get things like query speed, right? You can add kind of more performant column scan or table scanning to queries that were originally just going to be against your OLTP system. By giving it access to columnar data, you can do vectorized computing and you can do faster table scans if you're not going to hit an index, right? This also allows for augmented transactions, which is kind of like an industry buzzword, but an augmented transaction is essentially a transaction that has within the transaction an aggregation query or an analytical query that you don't want your transactional latency to depend on. Well, it's going to depend on it, but you want it to be fast so that your transaction can complete. Large joins too. This is a good way to get rid of some of your large join problems where you're passing huge tables over the wire. You can push down the joining operations to the storage in a lot of cases because of massively parallel processing at storage, which is another common feature of HTAP. Again, the unified API, we don't need to go into that again. Okay, so onto the talk is like really about, right? So evaluating HTAP, when you're evaluating any system, you kind of have to start by determining goals, right? So the goals of an HTAP system, at least as we purport them, is to have a single database experience. That's again to have a single interface for developers, and then a single kind of basically package deployment scheme for your backend engineers to make them both happy. Secondly, with HTAP, because we're now combining workloads, right? This is kind of not really done typically, at least historically. So we have OLTP and OLAP workloads in the same place. So what we want to do is prevent them from interfering with each other too much. So workload isolation is something we want to test for. Real-time and online analytics, we want our data to be fresh, right? So if it's going to be online, as my definition says, it should be in real time. So analyticals should be able to observe the latest transactional updates. When doing a performance evaluation, you want to define some metrics. So in this case, and leading into the tool I'm going to introduce, Wisconsin defined two core metrics here. The first one is called the throughput frontier, which basically measures the absolute possible throughput of the system from a transactional and analytical workload perspective. And then the second is a freshness score, which is essentially a measure of real timiness, but basically it's the time to be readable for every transactional value. And what this means is basically any transactional commit that where the timestamp of the commit is before the analytical query starts, all of those points should be readable, right? That was what we call a fresh data set. If any are unreadable, then there's some amount of staleness to it. And then in order to do this, we need to create a tool that can programmatically generate a bunch of tests for us. And that's what HATtrick is, and I'll talk about it in a little bit. So to the throughput frontier, don't get scared by the math notation. I get scared by it. It's there because it kind of needs to be, but the throughput frontier is essentially just a combination of tuple pairs of a number of transactional clients and a number of analytical clients at the same time, and the throughput that each of them are doing in total. So the inputs are the client number, transactional clients, and the analytical clients, and they can be moved independently of one another. And the output, or the result of the function, is essentially the throughput of both, right? So the number of completed transactions, the number of completed queries, analytical queries per second. Or it could be per minute, whatever you want to choose, whatever makes sense to you. So with this tool, you can do this test a bunch of times, and you can plot a bunch of different, potentially real world scenarios, right? Different amounts of workloads where you're not saturating your system. Because we're doing a benchmarking, though, we want to actually saturate the system and see like where can we like take this thing to, right? So all of these points here are just going to be your maybe random samples, maybe they're strategic, maybe you have customers or something that have specific workloads and you want to see if you can deal with them and where they fall. But we have this curve here. That's the frontier itself, and the frontier is basically the maximum throughput at any point at any number of transactional and analytical clients, respectively. So it might be a little confusing. The way we find this thing, right, is we can't do infinite tests. So what we do is we'll strategically pick some number of fixed amounts of transactional clients as well as fixed amounts of analytical clients to test with. So we'll start with, say, 0 transactional clients. We'll saturate the system with analytical workload and see how much throughput we can get, right? So we've basically figured that out. We plot that point, and then we move our transactional clients over to the right, increasing that, and then fixing it, and then increasing analytical client workloads as much as we can until saturation. And saturation is basically when throughput stops improving, right? So when we start to see a dip, as those lines are kind of indicating. And we continue to do that, and then we reverse it, and we then we do different fixed analytical client workloads, and we see what kind of transactional throughput we can get at saturation. So that's how we define that curve, right? And basically the way to look at this curve is that any other workload is going to fall underneath that curve. And if you are measuring multiple types of HTAP systems, if you see a frontier curve that's fully enveloping another HTAP system's frontier curve, you know that the one that fully envelops it is a more performant HTAP system. So that's an easy test. So lastly, this is not really required, but this is a nice thing to do. When you're doing those tests where you're drawing fixed transactional workloads and fixed analytical workloads, you can kind of monitor where things get weird, right? So if you're there may be, at low workloads, there may be fairly good resource isolation where if you increase transactional workloads, it doesn't affect your analytical and vice versa. But as you go further out, right, as you get closer to the frontier, there may be some wonkiness, which might kind of uncover possible troubleshooting scenarios or like weird workloads that you want to kind of identify later, and tell your customers like don't do this ratio of analytics to transactions. The perfect workload isolation is essentially a grid graph like this that's perfectly straight and like a perfect grid, right? Just all 90-degree angles. That's never going to happen in the real world, but the closer you can get, the best. So when you're looking at the frontier curves, what do you want to see? We have this thing called a proportional line, which is basically the relationship we've defined between transactional and analytical workloads and how they affect each other, or how they would affect each other. Sorry, if they were perfectly proportional, and that's basically the edges of your or the y and x intercepts of the frontier curve. Any frontier curve that falls along that proportional line means that you have some resource sharing, right? But it's a fairly predictable relationship between the two things. So as you increase your transactional workload, you can kind of understand where your analytical throughput might go. The second one here is perfect, not perfect, but it's really good, right? This is what we want to see. Anything towards that bounding box, the bounding box being your theoretical possible maximum throughput for both transactional and analytical clients if there was no resource contention whatsoever. And a line like this means that there's basically really good resource isolation as well as throughput at the same time. And then here is obviously not good, right? This is where there's not only resource sharing, but there's probably some kind of actual contention, like lock contention, where as you increase your analytical throughput, you sort of exponentially negatively impact your transactional throughput and vice versa. So you don't want to see a dipping frontier. Summarizes that. In case it wasn't clear, left is second best, middle is best. So the frontier role is basically to quantify absolute performance, indicate the workload isolation level, and then it gives you that bonus of being able to kind of find troubleshooting scenarios. It's not like something you necessarily need to do, but it can help. So okay, the second metric, freshness. This is the real timiness. These numbers here, to the right side of the colons on these points that we drew here, that is the time, it's a freshness score, and it's basically the time, and I'll explain this in a second, between the first not seen transaction commit time that happened, where the commit time was before the analytical query started. I know it's a massive mouthful. Let me just define some terms really quick. So freshness, I think I've kind of gone over this, but freshness is basically every transaction that has committed before the analytical query is started is readable by that query, right? That's fresh. Staleness is when there is any unseen committed values, okay? And some amount of staleness is usually fine, right? But it's just technically there's some staleness if there's anything like that going on. So okay, I might need to explain this twice. Who knows? But the way that this is calculated with the tool, which I'm going to introduce in a second, is you take the timestamp of an analytical query, and you check the data set for its transaction commit times. If there are any commits that committed before the analytical query started that were not seen, right? You take the first of those commits and you find that difference, and that's your freshness score. A freshness score above 0 seconds is an indicator of some amount of staleness. In some cases, you may find 0 staleness. You may find a 0 freshness score, which is good, which means that there is no red here. There's no unseen transactions. So in the interest of moving forward faster, I will continue, but feel free to ask me about this later if you want. So that kind of brings me to the HATtrick tool. How do they manage that, right? You might have some questions on how that is even possible. So the HATtrick tool is a really nice tool because it's specific to HTAP. It is a hybrid benchmarking tool that takes the best of the star bench, the SSB, which is from the star tree, which I think they're the Pinot folks, right? They're here. As well as the TPCC benchmark, which is, I think, the de facto, I think everyone agrees, is kind of the de facto OLTP benchmarking tool. It wraps those around. It uses the schema and the data set that the star bench uses, and then it adds the TPCC transactional style workload to that. The client does some cool things to make some of these tests possible. The first thing it does is when you're doing anything time related with these benchmarks, and you have a bunch of clients interacting with a server or a set of servers, if there's no globally synchronized clock, time can get super skewed, especially when you're taking precise measurements. So what they've done is they just said simplify it, track the time in each client, right? And then we'll realize that there's some network latency probably involved in the timings that we do, but at least if you take enough samples, we can kind of normalize for that. What it prevents by doing that is like time skew when you're comparing clients. The second thing it does, and this goes back to the freshness score and being able to see unseen points. Obviously, if you send an analytical client to a database and you want to see what the timestamp of an unseen point is, that's basically impossible, right? If the query can't see it, how can it know the timestamp? Well, the client tracks recent transactions and compares the analytical result and the timestamp of the latest point it got with the timestamp of the snapshot that it got with the transaction commits. And if there were any commits that happened before the timestamp of the analytical query that weren't returned by the analytical query, there's a freshness score to be calculated there, and they find that delta again. Sure. Say it again. Yeah, it's any of the clients, right? So any of the clients, and then the clients track an auxiliary table that it's kind of I'm going to give you a high level answer to this, but basically each client has a state for the entire client set. So the auxiliary table is tracked per client, but then when they do the calculation, they can see all transactions made by all clients.
I raised that because you mentioned there's no global in block, but the table that's stored in connection, there must be a timestamp there, and we compare the difference with the timestamp.
Yeah.
So would that be a
That's a good question. I don't believe so. But that might be one. That might be a question worth taking offline, because the one of the Wisconsin engineers is pretty easy for us to ping about stuff like that, with questions like that. I don't know the answer. Anyways, this is the, for if you really want to dive in, this is the source code for the HATtrick Benchmark tool. So the last thing I'll say about that is, when you're doing these benchmarks, I think it's pretty true for any benchmark against any database, but you have to make sure that you're testing correctly for the database that or the system that you're testing against. And in the case of HATtrick, it doesn't assume that you're working with a distributed system. So there's natural disadvantages to a distributed system when you're testing with the HATtrick. So you have to know that going in and configure your system appropriately. So that brings us to the TiDB section. So TiDB, just very briefly, not even going to give you the pitch. It's a disaggregated architecture, right? So every core component of TiDB is separated out into its core competencies. It's deployable all as one thing, but each process is handling its own core competency. So it is fundamentally disaggregated by nature, and this doesn't lend itself super well to a benchmark tool that's kind of originally designed for single node tests. So if any of you are TiDB users, you may have seen our key visualizer in the placement driver's UI, like the UI that ships with it. This is just, the x-axis is time, y-axis is your potential key space. If you have any activity along the x-axis and then there's a small amount of activity and there's a bunch of black space in that same time period, you have hot spotting essentially. So what happens is HATtrick will insert a bunch of data with monotonically increasing primary keys, right? And the way that we by default separate things out into regions, or like basically key space chunks, is by those keys. And so if they're in order, you're going to be inserting into one region at a time, which is ultimately one node at a time. And then when you're running analytical queries, at least especially at the beginning, you're going to be hitting just one node and one region at a time, right? So it's super unscalable and doesn't take advantage of the fact that you have however many nodes out there. Yeah. It's this. I might want an engineer here, but it's the regions are basically determined by a size, 96 megabytes, I think. Yeah, and for the recording, the question was, how does TiDB by default determine what these regions are? Like, how does it determine the key space that goes into a region? And so the answer was essentially that the regions are 96 megabytes by default, and so it'll by default it'll fill up a region and then split into another region as it overflows, right? But if you have actually going into the next slide, if you tell it that you don't want the key space to be distributed that way, that you want it to kind of be randomly scattered, right? There's multiple ways to configure it that way, and that can be, we can talk about that offline, and it's documented. Pretty simple to do, pretty easy change. Yeah, question was, those key spaces, are they maintained from the OLTP side to the OLAP side, right? To what we call the TiFlash servers? Yes, there's a direct exact mapping from TiKV regions to TiFlash. So when we configure it appropriately, we get a fanning out of the workload from a inserts, updates, and analytical query standpoint. and we take advantage of the distributed nature of the cluster. So once we do that, we get way better results, right? These are like very good results. We were happy with these. Basically, going back, we have our fixed transactional client count lines, right? So we fix a number of transactional clients, and then we just kind of throttle up the analytical client throughput, and then we see that the transactional throughput itself doesn't really change much. And then on the flip side, there's a little bit of downward pull on the analytical throughput when you increase transactional client numbers, but not much, right? So we basically have an almost perfect grid graph there if you were to overlay the two graphs there. And then we get the resulting frontier line, which is basically the shape of the bounding box and almost out to it. So it's basically doing as much as it possibly could with, you could probably tweak it to do a little better or, with future improvements, but this is basically as good as you can get with the goals of the HTAP that we had defined earlier, which are these, right? Provide a single database experience. So there's one endpoint. Your developers are working with one system. Your data is isolated. Your workloads are isolated. OLTP and OLAP can kind of work in tandem without negatively affecting each other. And then the data is real time. So that, I didn't even show this part. Sorry. The freshness scores were 0, right? So by definition, the way that this works, the way that the TIE flash works and the way it replicates data from the OLTP side is that when data is committed, it should be readable immediately, right? So basically, there is no staleness whatsoever by definition of how it's architected. So that last point there is checked. So that's all I have. When I'm 5 minutes over my time, maybe we'll do questions after Kanwoo goes. So we're splitting time. So Kanwoo has a 10-minute presentation that he's going to give.
So my name is Kanwoo, and I'm happy to give an overview on the collaboration efforts between UW-Madison and PingCAP on automatic cache tuning for HTAP systems. So with HTAP today, there's an increasing scale of data footprint you need to touch to handle all the transactional or analytics query today. As a result, there's an increasing demand on storage or memory systems that are scalable, high performance, large, and meanwhile cost effective. To meeting these demands, an appealing solution is to use a hierarchy of memory or storage devices. And as a result, caching who manage such memory hierarchies become an important aspect for HTAP systems. While there have been many well-researched solutions for caching for databases, HTAP we face unique challenges for building caching for HTAP because unique demands from HTAP systems. For example, first, nowadays many HTAP systems are deployed in cloud, and you need to pay for the results for your memory or caching. So the caching objectives not only need to cover performance, but also cost effectiveness. So how to balance the cost you pay for large cache space versus the performance you can get? This is an important question for HTAP systems on cloud. Also, for HTAP providers, nowadays you have more performance layers you can choose to build, as the storage hierarchies for you. You not only can choose traditional devices like DRAM or flash, you are having more emergent devices like CXL memory or persistent memory. While those are, providing, opportunities for better performance for hierarchies, it also poses challenges. You are having a more complex hierarchy today. So this raises the question of how can you automatically adapt your caching system to perform efficiently on all flexible future modern hierarchy. And finally, caching capacity for HTAP is not solely used by one workload and one client. It's now shared by different workloads such as analytics and transactional. Also, it can be shared by different tenants. So there's a question like, how will you do a good capacity allocation across different workloads and clients to achieve both overall fast performance and isolation, like we mentioned in the last benchmark work. So overall, there are many questions related to how to build a caching system for HTAP. So motivated by these questions, we have hence focused on building an efficient caching system for HTAP. And our key idea is to building towards an automatically tuned caching system. In particular, PingCAP and Wisconsin are interested in three perspectives. The first aspect is how can we automatically, sizing the caches to achieve a good balance for cost and performance. And the second, we're also looking into how to automatically tune your cache traffic towards different layers of modem hierarchy, so you can achieve the best performance out of the modem hierarchy devices. And finally, we're also looking into how to dynamically allocate space across different workloads to achieve both good performance and isolation. So to answer questions like what will be the benefits of such auto-tuned caching system and what will the tuning approach look like, today I will focus on one aspect, which is to do dynamic cache traffic tuning for exploit modem storage hierarchy. And this is work we published at BAT21. So as shown here, recently we have seen many new memory or interconnect techniques. And this techniques build, many new layers, which bring the performance gap between traditional DRAM and traditional hard drive layers, like shown in the figure. Excellent examples include our CXL memory or Optane persistent memory. Within such hierarchies, a major change is that there's less performance difference between labeling layers compared to that in traditional hierarchy. For example, thinking of DRAM versus a hard drive, more than 100 times difference before. So in these hierarchies, a problem we observe is maximizing hit rate is no longer sufficient to achieve optimal performance on modem storage hierarchy. Here, let's consider one simple hierarchy as an example. Let's think of 100 GB per second DRAM layer on top of a 50 GB per second CXL memory layer, and assume we have perfect knowledge of our workload, so we can achieve 100% hit rate. So at first glance, we might think this is great because we can cache everything in your fast DRAM layer, and we can achieve DRAM like 100 GB per second DRAM bandwidth. But at second thought, you will quickly realize that there's actually 50 GB per second large amount of CXL memory layer bandwidth wasted in this case. This is not what we want for best performance and cost effective. So ideally, what we want is we should be able to get the aggregated performance across all the layers in modem hierarchy. So what we want is we want to balance the access to all the layers in the hierarchy and hence achieve optimal performance. Moreover, because we have various workloads such as transactional and analytics, and the workloads can change over time. So what we really need is, and we will introduce next, is an automatically tuned cache traffic system to exploit the potential performance in modem storage hierarchy. So how to achieve this? We proposed an idea called feedback-based tuning for cache traffic tuning. So what we do is we first start with classic caching. By doing so, you will expect that the cache device or the faster device be warmed up, and we end the state 1 when we observe a relatively stable cache hit rate. And then we will try to look at whether bypass some workload or accesses from first fast layer to the second layer, whether it will improve overall caching performance. Here we define a bypass ratio as the ratio of cache hits which are bypassed to the second layer. And as you can imagine, the classic caching is basically do no bypassing or bypass ratio as 0. And our goal here is to adjust such bypass ratio so that we can achieve optimal caching performance. So what we do is, like shown in the figure, with current bypass ratio as x, and it starts from 0%, we will try both x plus delta and x minus delta, which indicates slightly more or slightly less bypass ratio. And kind of like the gradient descent approach, we will always move the X ratio towards the direction that can improve overall cache performance. And this is all done during runtime when you serve real workload. By doing continuous tuning like this, we were able to find the optimal ratio of a path, hence utilize both layers of performance, and also we will be able to adapt to dynamic workload. And finally, when hit rate radically changed or when we find out 0% bypass is always optimal, we will jump back to state 1 to restart this loop. So what are the benefits we get from this tuned cache traffic tuning? So what we get is we can now automatically utilize both layers performance in today's modern storage hierarchy. And our experiments on hierarchies of DRAM over Optane DC% memory and Optane SSD, which is a very low latency SSD, over traditional LAN SSD, we see cache performance improve by up to 30 and 50%. And some important properties of our auto-tuned caching approach is, as you can see, first, it's compatible with all existing caching implementations of policy. Second, we do not input any specialized knowledge of both the device you are managing and the workloads you will treat. So our automatically tuned caching system is easy to use. And finally, it's robust to dynamic workload. So today we covered the dynamic cache traffic tuning. As we overviewed slightly earlier, we are also looking to how to dynamically sizen the cache correctly for HTAP system. And also we are looking into perspective 3, which is automatically allocate space for different workloads and different clients for performance and good isolation. So overall, we believe HTAP puts unique challenges on efficient caching system, and we are building towards such automatically tuned caching systems for future HTAP systems. So finally, thank you, and all questions are welcome.